Bismillahirrahmanirrahim. I am Professor Jamil and you are watching YouTube channel. Today we are going to do an article about the Laplace transform, and the article is inverse Laplace transform. In the earlier videos we learned how to find the Laplace transform. This time we shall learn how to find the inverse Laplace transform, and the procedure is very simple. Let's first know what does it mean by the inverse Laplace transform. So here goes your heading for it: inverse Laplace transform. And let's start from the Laplace transform, which we know already. We know that this is an integral operator known as Laplace transform operator when it acts on some function like f of t, right? And you know this is an integral operator, Laplace transform operator, and the action of integral operator on any function ft is represented by these curly brackets, this and this. And what this Laplace transform perform for you? It gives you a new function, which is, for example, this big F, and a new variable s. And this fs is known as the Laplace transform of the function ft, right? Now, what we need to do? We need to find its inverse. And how we can find it? Look, this is the same operator, Laplace transform operator, but I am putting a -1 above it. This means inverse. So this will be read as inverse Laplace transform operator. So the sign -1 means inverse. So this is inverse Laplace transform operator. And let's apply this on, you may also name it. This is, now, this is, this symbol, 3 line mean identical, is the inverse Laplace transform operator, right? And let's now operate it on the Laplace transform. Let's operate it. L inverse acting on LFT, and same thing on the right hand side, L inverse acting on Fs, right? Now this is inverse of L. So whenever an operator and its inverse are multiplied together, they produce identity. So this you can write L inverse L is I, mean this is the identity operator, right? And so write I acting on f of t, and it gives you right hand side as such, Fs. Now, identity operator by definition is the operator which, when act on any function or any object, it leaves the object as such. So this I acting on ft will give you ft, right? So this is ft, and this is equal to L inverse of Fs. So this piece, this is known as inverse Laplace transform of Fs, right? This Fs. Fs is what? This is the Laplace transform. So for finding the inverse Laplace transform, what is essential? You should have the Laplace transform first, then apply the inverse operator on it, and it will give you the function, new function. And this new function will be known as inverse Laplace transform of Fs, right? Okay, so this is in fact the procedural equation which you must store in your mind. And what is the procedural equation? you should have the Laplace transform first in the form of fs, right? And then apply the inverse operator on it, and you will get a new function, and that new function will be named as inverse Laplace transform of fs, right? Now, for applying this procedure or this equation, you need to know the Laplace transform, and it is not possible that you know the Laplace transform of every function. There could be functions whose Laplace transform is not visible in the first place or in the first sight. Then what should we do? Here is the remedy. You have already calculated some of the Laplace transforms of the functions like this. You have found the Laplace transform of e to the power kt. This is 1 over s minus k, where s is greater than k. S is the new variable. Remember, the new variable is not always s. It can be named with any other symbol like x. So Laplace transform of e to the power kt could be 1 over x minus k, or it could be 1 over u minus k. U is the new variable. The new variable can be named with any symbol. This is very important to know, because it is not always possible, or it could be the case, that you are given Laplace transform not in the variable s. You may be given the Laplace transform in any other variable. You just need to identify which one is the variable in the Laplace transform. Like here in this case, this is the variable and k is the constant. This is the constant, t is the variable, right? Now, similarly, there is a second formula, Laplace transform of sine of kt, right? And this was k over s square plus k square, and again s greater than k. This is the condition. These Laplace transforms we have already found and calculated in a separate video. You may visit that video if you do not know these transforms. You can visit that video is made by me, right, on the Laplace transform. And in the third place, you know the Laplace transform of cosine of kt, and this is s over s square plus k square, and the condition is again same, s greater than k. Now, what is the difference between sine and cosine in the form of Laplace transforms? In the case of cosine function, there is the variable in the upside, and there is no variable for the case of sine function in the upside, right? Now, the new variable here is not always s. It can be changed. For example, Laplace transform of sine kt could be written as k over u square plus k square. K is the constant and u square is the variable. And Laplace transform of cos kt is this. And in place of the variable s, you can be given any other variable. For example, this could be the variable alpha over alpha square plus k square, right? And then you will write alpha is larger than k. Okay, so now if this function was sine hyperbolic function, then in case of hyperbolic function you have a minus sign here. Everything else is same. S square minus k square. And in case of cos hyperbolic function, you have s over s square minus k square. And similarly, for the case of hyperbolic functions, the variable s can be named with any other symbol, right? So these three formulas would be enough for you to compute the Laplace transforms of many other Laplace transform. These three formulas would be enough to compute the inverse Laplace transform of the Laplace transforms which would be given to you. Let's check. I have prepared some problems or questions for you. These are: find the inverse Laplace transform of these functions. It means these functions are the Laplace transforms, and of these Laplace transforms you need to find the inverse Laplace transform. Now, this question, for example, is not in the standard form. 1 over s minus k or 1 over s square plus k square and so on. But you can break these two factors into two fractions, and this method is known as method of partial fractions. So let's do this question by the method of partial fractions. Now, how the partial fractions are made? There is a standard procedure for finding out the partial fractions, and we do not wish to follow that standard procedure. In place of that procedure, we shall be following a shortcut method. And what is the shortcut? Look, this 1 over x plus a and 1 over x plus b. This, imagine in your head that you have written it as 1 over x plus a minus 1 over x plus b. The two factors are written separately with the minus sign between them. And then take their LCM. And what is the LCM? X plus a into x plus b. Now, when x plus b is simplified, you will have x plus b here. Sorry, x plus a will be cancelled and you will have x plus b minus this x plus b cancelled and you have x plus a in the upside. Now, this x will be cancelled and you will have b minus a. But you do not have in the actual question b minus a. So this b minus a, right, this is b minus a over x plus a, x plus b, and the left hand side is same. Now you can shift this b minus a on the left, and by shifting it on the left, look what you have. 1 over, this is 1 now, x plus a into x plus b. And now look, your given Laplace transform has been split into two fractions, and you know the Laplace transform of this now. This is Laplace transform of e to the power minus at. The constant is this. Look, in this formula, if this is a minus sign, then it will produce a plus. So the opposite sign comes here. Okay. So announce them. And what is the announcement? 1 over b minus a as such. And this is Laplace transform of e to the power minus a into t. T is the variable. And minus, this is the Laplace transform of e to the power minus bt. And the right hand side is same, no change in it. Now, this Laplace transform operator is a linear operator. It means it can be moved on the left of the constant. Linearity means the constant can be moved to the right of the linear operator, or if it is on the right, then it can be moved on the left. And for this time, we are moving this constant on the right of this operator, right? So this is linearity of the operator. Let's use it. Using linearity of operator L, this L is taken out. Look, this, and it is acting on this constant will be taken inside, and this is 1 over b minus a into e to the power minus at. This one, this L has been taken out, and this minus sign, this, and this constant moving inside, mean 1 over b minus a into e minus bt, and the operator L has been moved on the left. This is linearity. Okay, and the right hand side is again same, no change in it, x plus b. Now you need to take inverse transform of this one, right? And when you have completed this step, you do not need to write a new step. Instead, you can apply L inverse here and L inverse here, right? So that it becomes clear that now you are taking the inverse transform. So you have done two steps, and right here, using linearity of L and applying L inverse, we get, first you have used the linearity. Linearity means you have shifted the operator L on the left and the constant on the right of it. And the same here, the operator on the left taken common and the constant on the right of this. Okay, now this will be cancelled because this is the identity, and you can simplify it, e to the power minus at minus e to the power minus bt over b minus a, and this is inverse Laplace transform of x plus a and x plus b. So here is your answer, and you can make a reference that L inverse L is identity operator, right? OP for the operator. So this is the inverse transform of this question number 1. So the Laplace transform was given to you, and of this Laplace transform you have found the inverse, and this is this, right? Let's do the next question, question number 2. Now this question number 2, look, the question number 2, you have this Laplace transform and it contains the variable t, right? And a and b are the constants, but it contains two factors in the denominator, so you can make its partial fractions. Let's do this. And what is the method? Imagine that these denominators are separately written like this, 1 over t plus a, and put a minus sign, and 1 over t plus b. This is the very speedy way of finding the partial fractions instead of following the routine procedure. Okay, now this thing, and then take its LCM as I did in the question number 1. So take the LCM, t plus a into t plus b. Now t plus a will be cancelled, this, and you will have in the upside t plus b, and minus t plus b will be cancelled and you will have t plus a. Now do the simplification, a little simplification. When you expand these brackets, this is plus t and this is minus t, this will be cancelled, and you will have b, and this minus will make it minus a, and b minus a. So in the upside you have b minus a, but in the given question you do not have the constant, you have the variable t, but the variable here is being cancelled. You need to retain it here. Let's check how we can retain it. Look, if this piece is multiplied with the constant a, then it will give you at plus ab, and if you multiply this second term with b, then it will give you minus bt, which is different from at, and minus ba. This minus ba will be cancelled with this plus ba, and you will have a term in the form of t in the upside, right? So now your constant is being cancelled and you are having t in your numerator. And let's write the next step so that t becomes visible. This is at minus bt, that means a minus b into t, and plus ab and minus ab will be cancelled, and denominator is same, t plus a and t plus b. Now in the given question, or in the given Laplace transform, you have only t. This b minus a minus b is extra, so move it on the left. So left side is 1 over t plus a minus 1 over t plus b. Now take this a minus b on the left, so it is 1 over a minus b into, same thing, t plus b, and here you have t over t plus a and t plus b. You can also replace this thing with the function gt if you like. Okay, but I will not do this. I will keep it. Now 1 over t plus a. This is like 1 over s plus k. So this is the Laplace transform of exponential function. Similarly, this is the Laplace transform of exponential function. Now you identified that this is the Laplace transform and this is the Laplace transform, because having the Laplace transform is important for finding the inverse Laplace transform. So let's do the transforms. So in the next step here, 1 over, this is a minus b, and here this 1 over t plus a. Now the variable is t. In the Laplace transform, in place of s, your variable is t. So this is what Laplace transform of e to the power minus at. If this is plus, then the exponential will contain the opposite sign, mean minus. And minus this 1 over t plus b. This is the Laplace transform of exponential e to the power minus bt. And on the right hand side, there is no change. T plus a and t plus b. Now, again, this L operator is a linear operator. So linear, and the linearity of the operator means what? This constant can be moved on the right and this operator can be written on the left. Same thing here. So let's using linearity of L. So this is L acting on, this constant is moving on the right of L, in here 1 over a minus b into this function minus at, and minus this constant again here 1 over b a minus b into this e to the power minus bt and curly bracket, right? And the right hand side is same again, t over t plus a and t plus b. Now you have the Laplace transform, mean this given object which is a Laplace transform is in fact this Laplace transform, right? Now you need to take its inverse, and you can take the inverse here also using linearity of L and taking, and applying this L inverse operator we get. So now do this piece and apply L inverse. You can apply here. You do not need to write a new step, and you apply L inverse here, right? So this is identity, it will be cancelled, and you will have this can also be simplified, e to the power minus at minus e to the power minus bt over a minus b, and this is equal to L inverse of this function t plus a t plus b. So this is the inverse Laplace transform of the given function, this t over t plus a t plus b, right? Okay, this question has been done, mean the solution is complete. Now there is the third question, this one. This is the Laplace transform, right? And it contains d over dv, mean this function is being differentiated with respect to v. So v is your variable of the Laplace transform, and alpha is a constant here, right? And in this case, how can you find the inverse Laplace transform? For that matter, you first need to break this function into the form 1 over s plus k or 1 over s minus k. So let's do this carefully. This is d by dv of log of v plus alpha over v minus alpha, and this shows d by dv, again I am telling, This means that your variable of the transform is v. Now, apply the logarithmic property first so that you get little simplification. This is log of numerator minus the log of denominator. This is property of the logarithmic function. So minus log of v plus alpha, v minus alpha, right? Now take its derivative. So log will give you derivative 1 over v plus alpha, and it will give you 1 over v minus alpha. Now you know this is the Laplace transform of exponential function. It is like 1 over s plus k, right? And it is like 1 over s minus k. In place of the variable s, you have the variable v now. So this is Laplace transform of e to the power minus alpha t, and this is Laplace transform of e to the power alpha t, and the left hand side is same, no change in it, log of v plus alpha over v minus alpha, right? Now you have Laplace transform operator, and it has linearity property, and you using, let's write here, using linearity of the Laplace transform operator L. So d by dv of log of v plus alpha over v minus alpha, and it is equal to Laplace transform of this e to the power minus alpha t and minus e to the power plus alpha t, right? If there is no constant, it is 1. It is 1. Now what we have done, this one had, imagine that this one has been moved on right and L on left, 1 on right and L on left, and then L common in this way, right? So this is linearity, and now you can apply the L inverse operator, right? So right, and apply L inverse, we get what you get. Apply the L inverse here and L inverse here, right? And when L inverse will be applied, then you need to apply the curly brackets to show action of the operator, right? Now this L inverse L will cancel to identity, and identity will produce the same function as you are given. So this is in the next step, inverse Laplace transform of d by dv of log of v plus alpha over v minus alpha is equal to this function e to the power minus alpha t minus e to the power alpha t, because L inverse L is identity operator, right? Now you can report this answer as such as written here, or you can take the minus sign common and turn this into the hyperbolic function. Let's do this. Minus sign out, and this is e to the power alpha t minus e to the power minus alpha t, and then the next step, divide it by 2 and multiply by 2, and within the parentheses you have sine hyperbolic alpha t. So this is, on the left is L inverse of d by dv of log of v plus alpha over v minus alpha, and this is equal to minus 2, and this one is sine hyperbolic alpha t. So this is the inverse Laplace transform of your given Laplace transform, right? So this has been completed. Still I have more questions for you to practice how to calculate or compute the inverse Laplace transform. Let's check more questions. These I have on other board here, right? Find inverse Laplace transform of 3 questions have been done already, and then number 4, number 5 and number 6. So let's do this. Let's do these questions. Solution, go to question number 4. Here you have again two factors in the denominator, which means you should do the partial fractions. And imagine these two have been written as separate fractions, mean 1 over first factor, then minus sign as I have told you, and 1 over the other factor, beta square. Look, your variable is what? HU, mean H is the function of U. So U is the variable of the transform. Because you have been told you need to find the inverse Laplace transform. It means whatever is given to you is the Laplace transform. And the Laplace transform has the variable U now. So alpha and beta are the constants. Okay. After then identifying this, you write the two fractions in this form and then take the LCM. U square plus alpha square and U square plus beta square. Now U square plus alpha square will be cancelled from here and you have this U square plus beta square minus this will be gone and you have this piece up U square plus alpha square. Now when simplified, this plus U square will cancel with this minus U square, and in the upside you will have beta square minus alpha square. So in the numerator you have no U, you have beta square minus alpha square, and you have no U, right? So this is correct. But there is a constant beta square minus alpha square. This is an extra constant and it can be moved on the left. So let's write it one time more. This is beta square minus alpha square over this, and the left side is same, no change, and move this constant on the left so that you have 1 over this as given in your original question or statement. So let's do this here. Here 1 over beta square minus alpha square into 1 over U square plus alpha square, this piece, and minus 1 over this thing U square plus beta square, bracket closed, and on the right hand side here you will have 1 divided by these two factors U square plus alpha square and U square plus beta square. Now look, this is like 1 over s square plus k square. It means this is the Laplace transform of sinusoidal function sin kt. In place of k you have the constant alpha. So this is the Laplace transform of sin alpha t. But you have here a constant because Laplace transform of sin kt is k over s square plus k square. So one constant is missing here. You can manage that in this form. Look, you can do this step here. Alpha multiplied and then divided by alpha. Now this thing is the complete Laplace transform of sin alpha t. Similarly here beta is missing and beta, and then divide by beta, and minus sign is already there. This is the minus sign, right? Okay, and you can do this in your exam paper, 2 steps in 1 line. Okay, now use this sign. This implies 1 over beta square minus alpha square into 1 over alpha, and this one is the Laplace transform of sine alpha t minus this 1 over beta, and within the blue brackets this is Laplace transform of sine of beta t, and the right hand side is same, no change in it, u square plus alpha square u square plus beta square, right? And there is a bracket here as well, this square bracket closed. Now you use the linearity property of the operator. You are guessing the procedural steps are same everywhere. So when you have practiced these questions, you will be able to find Laplace transform of any given Laplace transform. Now, right, using linearity of L. Now, what is the linearity? The same. The constant can be moved on the right and the operator on the left. And then here, this is whole constant. So it will be written on the right of L and L on left. And same here, L on left. So L is here and it is acting on 1 over beta square minus, it is beta square minus alpha square now? Okay, beta square minus alpha square into this 1 over alpha into this sine of alpha t minus this constant will move here 1 over beta square minus alpha square into this 1 over beta and into this sine of beta t, right? And there is a curly bracket here and equal to this piece, same, no change here, same thing. Okay, now you need to take its inverse Laplace transform, and let me do it on this side so that I have bigger space to complete the whole step. Apply, you may also apply here as well if you have written this factor. Let me do this. Write this factor again. 1 over u square plus alpha square into u square plus beta square, and declare and here, declare here and apply L inverse we get. Now apply L inverse. Let me apply it in the red. L inverse here and L inverse here, right? Now this will cancel, and in the next step you have your answer. This cancels to give the same function because this is an identity. So, and you can do some simplification over here. This 1 over beta square minus alpha square can be written as this, beta square minus alpha square into this is sine alpha t divided by alpha, this alpha, and minus this is sine of beta t divided by beta, this beta, and on the right you have inverse Laplace transform of this thing, u square plus alpha square into u square plus beta square, right? So this is the inverse Laplace transform of the transform which was given to you in the form of question number 4, right? So you have the inverse Laplace transform of the question number 4. 2 more questions are left. Let's do them also. And the planning is same. Solution to the question number 5. Here you have again 2 factors in the denominator, but look, omega is a function of k. Name of the function is omega and the variable on which it depends is k. So your k is now variable of the Laplace transform. That means this lambda and mu are constants and k will be treated as variable, right? Okay, so write this in the form of two fractions, 1 over k square plus lambda square and minus 1 over k square plus mu square, and then take the LCM. Let's take the LCM. And what it gives you, k square plus lambda square into k square plus mu square. My purpose here for solving more than one question is to make you familiar with the idea of identifying the variables in the Laplace transform so that you can find the inverse Laplace transform. So this one over this factor gone, and you will have this k square plus mu square and minus, when this is gone, you will have this factor minus k square plus lambda square, right? Now look, this plus k square and minus k square will cancel, right? And you will have the constant mu square minus lambda square in the upside. But in the given function, you have the variable in the upper portion of the question, mean in the numerator, right? So you need k square here, and the strategy is very simple. Multiply this by lambda square. Now you have lambda square k square plus lambda square mu square, and multiply here by mu square. You will have minus mu square k square and minus mu square lambda square. But this minus mu square lambda square will be cancelled with this plus lambda square mu square, and you will have a term in k square in the numerator, right? So let's simplify. This is equal to this, and the next step is, now this lambda square k square and minus mu square k square means lambda square minus mu square, and k square is common from the first two, and the constant lambda square mu square minus mu square lambda square is cancelled. So you have this in the numerator, and the denominator is same, no change, k square plus mu square, and the left hand side is again same, no change here, k square plus lambda square minus this k square plus mu square. Now look, in the given function for question number 5, you have k square in the numerator only, this k square, this part is extra, so you can move this constant on the left hand side, right? Let's do this in the next step. Here, this is the space where the next lines will be written. This is taken on the left, so it is 1 over lambda square minus mu square into this piece, these two fractions, 1 over k square plus lambda square and minus 1 over this thing, k square plus mu square, and on the right hand side this is gone to the left, so in the numerator you have only k square, and in the downside you have these two factors, k square plus lambda square and k square plus mu square, right? Now look, this is the form 1 over s square plus lambda square, mean this is 1 over s square plus k square. So it should be the Laplace transform of sine function, but for the case of sine function, this constant lambda should appear in the numerator, and the missing of the constants can be compensated like this. You can multiply by lambda and you can divide by lambda here. Now this is the Laplace transform of sine lambda t, right? And in the green portion, this here the constant missing is mu, right? And when you have multiplied with mu, you should divide by mu, right? And this within the green parentheses, you have Laplace transform of sine mu t. In place of k, you have mu, right? Okay. And by doing this, let's write the next step. You have 1 over lambda square minus mu square into 1 over lambda, and this one is the Laplace transform of sine of constant into variable, minus this is 1 over mu, this green, and within the green parenthesis you have the Laplace transform of sine, the constant is mu and variable is t, and bracket closed. And on the right hand side, same thing, no change, k square plus lambda square and k square plus mu square. Now you have the Laplace transforms, and you can apply the linearity property of Laplace transform now. So using linearity of the Laplace transform operator, and that means this and this constant can be moved on the right of L, and L will appear on left. Same, this constant multiplied with this will move on right and L on left, and then L is common. This step has also been done again and again, right? And do this. Laplace transform acting on this constant into this constant into this function lambda t, minus this constant multiplied with this constant lambda square minus mu square into 1 over mu, this mu, and into this function sine of mu t, bracket closed, and the right hand side is still same, no change in it, k square plus lambda square into k square plus mu square, right? Now you know the Laplace transform. This Laplace transform is in fact this Laplace transform, and now you apply the inverse operator on it, and this you can do in the same step, linearity and apply L inverse. Let us apply L inverse in the same step. When you have completed this step, then imagine you are doing the next step in this line, in the blue step. You have applied L inverse on the left, and you have applied L inverse on the right. And this is the inverse Laplace transform of your given Laplace transform, right? Okay. And in the next step, this cancels, and you have, take this constant common, 1 over lambda square minus mu square, and within the bracket you have sine lambda t over lambda minus sine mu t over mu, and it is the inverse Laplace transform of the function k square over k square plus lambda square into k square plus mu square. Done. This is the Laplace transform of, this is the inverse Laplace transform of this given Laplace transform, right? So this question has been done, and you have been left with the last question, this one. And look, in this question, this is the Laplace transform, and you need to find its inverse. And for that case, you look, there are two factors in the denominator, so we should first break these two factors into single fractions, right? Mean partial fractions. And identify the variable. This is a function which depends on omega. So omega is your variable, and this time k is a constant. So while doing this problem, you will treat k as the constant and omega is your variable. This is k square. This is k square, right? This is k square. This is k square. So let's do this last problem. Solution to the problem 6, and you need to write them as separate factors, mean 1 over omega, this is factor number 1, and then minus 1 over omega square plus k square, right? And then take their LCM, and this is omega into omega square plus k square, right? And this omega gone, this, and you have omega square plus k square minus this omega square plus k square gone, and you have only omega. Now look, there is no simplification in the numerator, and this is quite different from the given function, right? And what is in the given function? There is only the constant k square in the numerator. There is no variable. So you need to make this omega square vanish, and this will be possible when you have omega square here. And how can you get omega square here? Look in this. If there was omega over here, then this omega square plus k square will cancel, and this omega will be multiplied with this to give you omega square. Appreciate this trick. Otherwise, if you follow the routine procedure, it will take a lot of time for making the partial fractions, right? Now omega square is cancelled and you have k square in the upside, just as you have in your given question. So let's check the next step. This is k square over omega into omega square plus k square, and this is 1 over omega minus 1 omega over omega square plus k square. Now look, this is like 1 over s. This is like 1 over s, and this is the Laplace transform of 1, because Laplace transform of 1 is 1 over s, and in place of the variable s, you have the variable omega now. And this is omega square, and in the upside you have omega square. So this is like the form s over s square plus k square, right? So this is the Laplace transform of cosine function, cosine of k t. In place of t you have, sorry, kt, yes. So write the Laplace transforms in the next line here. Again, this piece, this is, if in the denominator you have s square, then you have s here, and in our case we have here omega square, and here is we have omega. So this is the Laplace transform of cos kt. Okay, so here this implies 1 over omega. This is Laplace transform of 1 minus this minus, and this is what? Laplace transform of cos of kt, right? K is your constant, and the right hand side is same, no change in it. This is k square over omega into omega square plus k square. Now you can use the linearity of L again, using linearity of the operator, linearity of the operator L, and this is L acting on 1 minus this. This L has been taken just like as common, cos of kt. and on the right hand side no change, the factor is written again, sorry, the part is written again. Okay, now you take the, this is the Laplace transform and this is in this form, right? And that's right, and apply L inverse. Let us now apply L inverse, mean take the inverse Laplace transform. So L inverse here and curly bracket to show the action of L inverse, right? And this L inverse, L is again identity and it will give you the same function, no change in it. So 1 minus cos of kt is equal to the inverse Laplace transform of k square over omega into omega square plus k square, right? This is the inverse Laplace transform of your given function. This is the answer. If you like, this 1 minus cos kt is like 1 minus cos theta, and you can apply the half angle identity. It is 2 sine square theta by 2. In place of theta, you have kt. Or this is 2 into sine square theta by 2. Theta is your kt. So kt by 2. And this is equal to L inverse of k square of omega into omega square plus k square, right? So you can express your answer to this question in this form. This is this final solution of your last part of the problem, right? Question number 6. I hope you have good knowledge now how to find inverse Laplace transform. And the method is what? Whatever the function is given to you is the Laplace transform. And you need to simplify that Laplace transform so that it looks like in this form, right? And many others. Thanks for watching. Sorry, please, these exercises are not enough. Look, there could be a minus sign here. This is u square minus alpha square. And if there is a minus sign, then you will have hyperbolic functions in place of the simple trigonometric functions. So these, out of these 6 questions, there are 5 questions. There is only one question like this, which does not contain a factor. Okay, this also contains this v plus alpha. You can write v minus alpha up and v plus alpha down and then compute the question again, right? So I suggest you should try these questions with signs change between them. 1 over x minus a into x minus b, or 1 over x plus a into x minus b. This is t plus a into t minus b, t minus a, t minus b, right? So from these 6 questions you can try to solve many more than 6 questions here by just changing the sign. And I suggest you should practice these questions so that you get a good idea of finding the inverse Laplace transform when the Laplace transform was given to you, right? Thanks for watching. Please like, share and subscribe this channel so that such solutions come to you in the first place. Thanks for watching.